Welcome to this explainer. Today, we're going to take that intimidating alphabet soup of Linux file permissions and translate it into clear, totally actionable knowledge. Look, whether you're managing some massive, complex server infrastructure or just tinkering around with a home lab on the weekend, understanding exactly how Linux protects its files is pretty much the absolute bedrock of system security. All right, let's take a quick look at our roadmap. We're kicking things off by cracking the permission code. Then we'll see what read, write, and execute actually do in practice, master the magic of numeric math, and finally, we'll wrap up with the essential commands and some critical best practices. We have all been there, right? You're just trying to run a quick script, maybe edit a config file, or even just navigate into a directory, and boom, you're hit with the universal frustration of a locked-out server. Permission denied. It is incredibly infuriating. But honestly, it just means the Linux security model is doing exactly what it was built to do. So let's uncover exactly why this happens, and more importantly, how you can take control securely without just, smashing the door down. Okay, let's jump right into section 1, cracking the permission code and breaking down that 10-character string. Whenever you run a long list command, like ls-l, you're immediately greeted with this 10-character string. Think of it like a secret security code attached to every single file on your system. The very first character simply tells you what you're actually looking at, so you'll see a dash for a regular file or a D for a directory. Right after that, the next 9 characters are split up into 3 distinct, mutually exclusive groups of 3. The first 3, they dictate what the user who owns the file can do. The next 3 define the permissions for the group that owns it, and those final 3, those are for absolutely everyone else on the system, the others. What's really fascinating about this process is that the Linux system basically acts exactly like a club bouncer at an exclusive VIP event. When you try to access a file, Linux runs through this very strict top-down checklist. Step 1, are you the owner of this file? If yes, boom, it grants you the owner permissions and immediately stops checking. You're in. If not, it moves on to step 2, are you in the group that owns the file? If yes, you get the group permissions, and again, the bouncer stops checking. Now, if you fail both of those checks, you get thrown right into the general public line, the others category. You literally cannot be covered by more than one category at a time. It's a totally mutually exclusive system. Moving smoothly along to section 2, read, write, and execute, and how these permissions behave completely differently depending on the context. So this right here is a massive stumbling block for a lot of administrators. On regular files, permissions make total sense, right? Read lets you view the contents, write lets you modify the file, and execute lets you run it as a program or a script. Easy. But directories, they interpret these exact same permissions in a totally different way. On a directory, read simply lets you list the files inside it. Write allows you to create, move, or delete files within that folder. So the absolute crucial takeaway here is that execute on a file means running a program. But on a directory, it simply means you have the right to access its metadata, use the cd command to enter it, or pass through it to reach a subdirectory. If you don't have execute permission on a directory, you can't even add a file to it, because you literally can't access the metadata to make that change. Next up, section 3, the magic of numbers. Let's demystify those octal values. If you find dealing with all those symbolic letters a bit clunky, you're going to absolutely love the numeric or octal notation. It basically turns setting permissions into a really satisfying math trick. Every permission is assigned a specific number. Read is worth exactly 4. Write is worth 2. Execute is worth 1. And no permission at all, that's just represented by a dash, which is a big ol' 0. By simply adding these values together, you can calculate the exact, precise permission level for any user category. It is such an elegant system, because every single combination of numbers from 0 to 7 represents a totally unique set of permissions. There's zero ambiguity here. Let's look at what a perfect score looks like. If a user owner is granted read, write, and execute permissions, you just do the math. Add 4 for read, plus 2 for write, plus 1 for execute. And what does that give you? A perfect 7. So whenever you see a 7, you immediately know it means total, unrestricted control for that specific category of user. And once you know this math, you can instantly decipher configurations out in the wild. For example, a permission set of 755, which is super common for web server directories, means the owner gets a 7, so read, write, execute. The group gets a 5, which is just 4 plus 1, meaning read and execute only. And others, they also get a 5. What about 644? That's your standard everyday file. The owner has a 6, read and write. Group and others just have a 4, which is strictly read-only. Or take 400. That is a highly restrictive setting for super sensitive things like SSH keys, where absolutely no one but the owner can even read the file. All right, Section 4, taking control and ownership. Now that we speak the language, let's explore the actual commands to secure your system. The core utility you're going to use here is chmod, which simply stands for change mode. And you've got a lot of flexibility with how you use it. You can stick to symbolic mode, say typing chmod u plus w to explicitly add write permission for the user owner. Or if you want to be fast and incredibly precise, you just drop in that 3-digit numeric code. Something like chmod 755 sets all the permissions for user, group, and others instantly in one swift stroke. It's a real game changer. But hey, sometimes the permissions are actually fine, you just happen to have the wrong owner. That's exactly where chown, change owner, comes into play. You can use it to change just the user, or if you use a colon, you can change both the owner and the group simultaneously. Something like chown user : group. And here is a massive pro tip for you. The capital R flag applies these changes recursively. If you're managing collaborative web hosting setups, using chown-R to assign an entire folder structure to a specific developer group is an absolute lifesaver. But be careful, running a recursive command in the wrong directory can completely mess up your whole system in seconds. Which brings us to our final section, Section 5, Best Practices and Pitfalls. It is time to talk about stopping the permission sledgehammer. Okay, we absolutely have to talk about the 777 sledgehammer. When an application just isn't working and you keep getting that annoying permission denied error, the temptation is so strong to just run chmod 777 and make the problem magically go away. Please never, ever use chmod 777 as a sledgehammer to fix a locked door. It literally grants read, write, and execute permissions to absolutely everyone on the entire system. It completely, utterly exposes your server, your application, and your sensitive data to unauthorized access and malicious modification. Instead, take a breath, figure out exactly which user or group actually needs access, and grant only what is strictly required. Actually, if you find yourself reaching for 777, there's a good chance what you really need is an advanced special permission instead. Linux has some incredibly powerful tools up its sleeve, like SUID or set user ID. When you apply this to an executable file, the program runs with the privileges of the file's owner, not the user who's currently running it. A classic example of this is the password change command. Obviously, regular users need to be able to change their own passwords, but they absolutely should not have raw write access to the system's core password file. SUID allows for that temporary, elevated access securely without compromising your total system security. Let's look at another brilliant special permission, the sticky bit. Now, this one is specifically a directory-level permission. Imagine you have a shared directory, like the /tmp folder, where all users need write access so they can create temporary files. Well, without the sticky bit, any user could just go in and delete anyone else's files in that folder. Chaos, right? By adding the sticky bit to the directory, it ensures that while everyone can write to the folder, a file within it can only ever be deleted by the specific person who created it. It perfectly stops users from accidentally or, maliciously wiping out each other's hard work. So, as we wrap things up today, just keep these golden rules in the back of your mind. Always apply the principle of least privilege. Start with the absolute minimal permissions and only add what is strictly necessary. Do use Linux groups to manage your collaborative projects efficiently. On the flip side, don't avoid standard security practices just because it's convenient in the moment. And always double-check those recursive commands to make sure you don't accidentally over-restrict a directory and break your web server's access to vital files. It's all a balancing act. And that brings us to the end of our dive into the Linux file system security model. So as you head out, I want to leave you with this one provocative question. Who currently holds the keys to your most sensitive data? Seriously, take a moment today to log into your server, run a quick ls-l on your vital directories, and actually read through those permission strings. Because deeply understanding who has read, write, and execute access, well, that is your very first line of defense. Keep exploring, keep learning, and keep those systems secure.